24 billion kilometers from where you are sitting right now, a machine older than disco is sending back numbers that should not make sense. It takes light more than 20 hours to travel that distance. It takes the machine's own signal, crawling at that same impossible speed, even longer to reach the dish that is straining to hear it. And when scientists finally decoded what it was saying, the room did not erupt in celebration. It went quiet, because the numbers described a place that, according to every model built over the last 60 years, should not exist in the way it actually does. Something out past the edge of the sun's reach is behaving in a way nobody predicted. And the strangest part is this: the machine that found it was never designed to make this discovery at all. Its name is Voyager. There are two of them, launched within weeks of each other in the late summer of 1977, riding a once-in-175-year alignment of the outer planets that would let a single spacecraft slingshot from Jupiter to Saturn to Uranus to Neptune using almost no fuel. That was the mission. See the giant planets up close, photograph their moons, then, quietly, drift into the dark and stop mattering. Nobody who built Voyager expected it to still be working half a century later. Nobody expected it to become the only human-made object to physically touch the space between stars. And nobody expected that touching that space would break as many assumptions as it confirmed. It keeps you warm. The sun is not just a source of heat. It is the center of a bubble. A colossal, invisible bubble made of charged wind of protons and electrons called the solar wind. This bubble is called the heliosphere, and it is almost incomprehensibly large. It swallows every planet, every moon, every asteroid you have ever heard of, and it keeps expanding outward until, eventually, the pressure of the solar wind can no longer overpower the thin, cold gas drifting between the stars. At that boundary, the wind stalls. It piles up, and beyond it lies something scientists call the interstellar medium, the ancient, diffuse material left behind by exploded stars, the space between star systems, the true edge of home. For decades, this boundary existed only in equations. Scientists knew it had to be there. They argued for years about how far away it was, what it would look like, and what would happen to a spacecraft that reached it. Then, on the 25th of August, 2012, after traveling for 35 years and more than 11 billion miles, Voyager 1 crossed it. The readings were unmistakable. The density of particles around the spacecraft jumped by a factor of 40 almost overnight. A signature so clean it left little room for doubt that the spacecraft had left the sun's bubble entirely and entered true interstellar space. It was, by any measure, one of the great milestones in the history of exploration. A single machine, built before most of the engineers currently monitoring it were even born, had carried a piece of humanity's curiosity past the edge of its own star system. But this is where the story should have ended, and did not. Scientists had a working theory of what interstellar space would look like once Voyager arrived. Colder, calmer, a place where the fierce turbulence of the solar wind gave way to a quiet, steady medium, its magnetic field pointing in one predictable direction, its plasma settling into values that matched decades of remote calculations. That was the expectation. That was what the models, built from radio astronomy, from theoretical physics, from every scrap of indirect evidence gathered since the 1960s, had predicted. And for a while, it seemed to be roughly correct. Then came the magnetic field data, and it did not point where it was supposed to point. The direction of the interstellar magnetic field, measured directly by Voyager for the first time in history, differed from other independent estimates by more than 40 degrees. 40 degrees is not a rounding error. 40 degrees is the difference between a hallway and a completely different room. Researchers proposed that Voyager might simply be moving through a region where the field itself had been bent and distorted by its collision with the heliosphere, the way a rubber band stretched around a beach ball gets deflected around its curve. That explanation helped, but it also revealed something uncomfortable. The boundary between our solar system and the galaxy is not a clean line on a map. It is a churned, distorted, dynamic structure, shaped by forces that are still not fully understood, even after direct measurement. Then came the plasma. Voyager 2, following its twin out through a different exit point in 2018, carried something Voyager 1 no longer had after one of its instruments failed decades earlier, a working plasma science instrument, capable of directly measuring the density and temperature of the charged particles around it. What Voyager 2 recorded, and what later analysis of Voyager 1's data confirmed independently, was that the plasma in interstellar space is measurably denser than solar wind plasma, exactly as theory predicted. But both spacecraft also detected something the models had not fully accounted for: a slight compression of plasma density right at the inner edge of the boundary, on both sides of it, as though the heliosphere itself were being squeezed from both directions at once. Scientists confirmed the observation was real. Independent instruments agreed with each other. But nobody could fully explain why the compression was happening, or what was driving it, on either side of that boundary. And then there was the heat. Beyond the heliopause, instruments recorded plasma temperatures reaching tens of thousands of degrees, hot enough that, described without context, it sounds like Voyager should have been vaporized on contact. It was not. The reason is one of the strangest and most beautiful quirks of physics in the entire story. Temperature and heat are not the same thing. In a region so sparse that particles are separated by enormous distances, each individual particle can carry enormous energy, technically making the plasma hot, without there being enough particles packed together to actually transfer that heat into anything solid. Voyager passed through fire that could not burn it, because the fire had almost nothing to burn with. It is one of those facts about the universe that sounds like a contradiction until you understand it, and then it becomes something more unsettling. Proof that our intuition, built entirely inside a thick, dense atmosphere, breaks down completely once you leave it. Long before any of this was measurable, ancient civilizations already sensed that the sky was not simply a ceiling. Babylonian astronomers tracked planetary wanderers against a backdrop of fixed stars and built calendars around cycles they could explain. Polynesian navigators crossed thousands of miles of open ocean using nothing but starlight, wind, and swell, treating the night sky as a chart of a world far larger than their islands. They had no concept of a heliosphere, no notion of plasma or magnetic fields, but they understood, in their bones, that the visible sky was a boundary behind which something vast and largely unknown continued. What has changed is not the intuition. What has changed is our ability to send an actual instrument out to test it, and to discover again, and again, that the instrument finds something more complicated than the intuition ever guessed. This is a pattern that repeats throughout the history of astronomy, and it is worth sitting with, because it tells you something about how discovery actually works. For centuries, scientists assumed the edge of the solar system was defined simply by the outermost planet, wherever that happened to be. Then came the recognition of the Kuiper Belt, a vast ring of icy bodies beyond Neptune, home to Pluto and thousands of smaller worlds, extending the practical boundary of the solar system far past what anyone had imagined in the era before telescopes could resolve such faint, distant objects. Beyond that lies the theorized Oort cloud, a spherical shell of icy debris thought to extend roughly halfway to the nearest star, the presumed source of long-period comets that occasionally fall inward toward the sun after spending unimaginable stretches of time drifting in near-total darkness. Even the Oort cloud remains, to this day, unconfirmed by direct observation. It is inferred from the behavior of comets, the same way the heliopause was inferred for decades before Voyager touched it. Somewhere out there, past even that theoretical shell, orbital anomalies in a cluster of distant icy bodies have led some researchers to propose the existence of an undiscovered planet, sometimes called Planet 9 or Planet Y. Its gravity tugging on the outer solar system's smallest residents without ever having been directly seen. A new observatory in Chile, equipped with the largest digital camera ever built for astronomy, is now conducting a 10-year survey specifically designed to either confirm or eliminate that hypothesis once and for all. Every layer of the solar system's outer structure, in other words, was first guessed at, then argued over, and only later, sometimes decades later, confirmed or overturned by direct evidence. That history should change how you hear the word confirmed in any headline about space. Confirmation rarely arrives all at once in a single triumphant announcement. It arrives in stages, through instruments failing and being replaced, through data being reanalyzed years after it was collected, through scientists publicly disagreeing with each other for years before a consensus finally settles. The compression at the heliopause is confirmed. The 40-degree magnetic field discrepancy is confirmed. The unusual chemistry of 3I Atlas is confirmed. What is not confirmed, and what may not be confirmed for years, is why any of it is happening. That gap between a measurement being real and a mechanism being understood is where genuine scientific mystery actually lives, and it is a very different thing from speculation. Mystery, in this sense, is not the absence of evidence. It is an abundance of evidence that has not yet been fully explained. It is tempting, when a story involves an aging spacecraft, an unexplained magnetic field, and an object visiting us from another star, to reach for the most dramatic possible explanation. Search the internet for either of these topics, and you will find no shortage of claims that Voyager has detected evidence of alien engineering, or that 3I Atlas is secretly artificial, propelled by something other than the outgassing of ice under sunlight. Reputable astronomers, including those who study interstellar objects for a living, have addressed these claims directly and repeatedly, and the answer has been consistent. The chemical and orbital behavior of 3I Atlas is fully consistent with a natural comet, one shaped by an unfamiliar but entirely physical formation environment, and Voyager's anomalies are consistent with the physics of an imperfectly understood plasma boundary. not with any signal, structure, or transmission of unknown origin. None of this makes the true story less remarkable. In some ways, it makes it more remarkable because it means the universe does not need embellishment to be strange. The real, verified, peer-reviewed data is already stranger than the myths built on top of it. None of this, on its own, proves anything exotic. No alien signal, no secret message, no confirmation of intelligent life. Scientists have been careful publicly and repeatedly to say exactly that. But taken together, these findings form a pattern, and the pattern is this. Every single assumption about what lies at the edge of our solar system has needed to be revised, sometimes dramatically, the moment real instruments actually got there. Not because the original theories were foolish, because theory, built from a distance of billions of miles using only light and radio waves as messengers, is always an approximation. Reality, once you touch it, is stranger and more layered than the approximation ever was. And there is one more discovery from the Voyager mission that deserves its own moment because of how quietly astonishing it is. One of Voyager 2's particle instruments detected something scientists nicknamed a leak, a small but measurable trickle of particles from inside the heliosphere, slipping outward through the boundary into interstellar space, as though the hull of a ship sailing through a sea were not fully watertight. The heliosphere is supposed to be humanity's shield, deflecting a significant portion of the dangerous high-energy cosmic radiation that constantly bombards our galaxy. And it does shield us, but imperfectly, and the imperfections were never predicted with this kind of precision until a 50-year-old spacecraft flew directly through the seam. Here is where the story widens, because Voyager is not the only thing raising these questions right now. In recent months, an entirely different kind of visitor has forced scientists to ask the same uncomfortable question from the opposite direction. What exactly is out there, and how well do we really understand it? Its formal name is 3I Atlas. The I stands for interstellar, and the number 3 means it is only the third object ever confirmed to have originated outside our solar system entirely, born around a star that is not our own, ejected into the emptiness between systems, and now, after who knows how many millions or billions of years drifting through the dark, passing briefly through our own cosmic neighborhood before continuing on a path that will carry it back out, never to return. Objects like this are almost unbearably rare from our vantage point. We have only confirmed 2 others in all of recorded astronomical history: Oumuamua in 2017 and Borisov in 2019. Each one is a message from a chemistry we did not write, delivered by pure gravitational chance. When the James Webb Space Telescope turned its infrared instruments toward 3I Atlas, it captured something no telescope had ever captured before: the first detailed mid-infrared chemical fingerprint of matter from another star system. And the fingerprint was strange. Compared to comets that formed here in our own solar system, 3I Atlas is releasing dramatically more carbon dioxide relative to water and unexpectedly high levels of methane. In our solar system's comets, that particular chemical balance is rare. It suggests this object condensed billions of years ago in an environment very different from the one that built the planets you are standing on right now, around a star we may never identify, in a system we will likely never see. As it continued moving away from the sun and cooled, its water production dropped sharply, exactly as physics would predict for any comet losing the sun's heat. That part was expected. The underlying chemistry was not. Scientists have been careful here too. The unusual chemistry does not indicate anything artificial, and it does not indicate life. What it indicates is diversity, proof that the raw ingredients drifting between star systems can be assembled in combinations we do not see at home. A reminder that our own solar system's chemistry, the exact recipe that eventually produced oceans, atmospheres, and eventually you, may be one version of many, rather than a universal default. Put these 2 threads together, the Voyager anomalies and the interstellar visitor, and a larger, more uncomfortable idea starts to take shape. Our solar system is not a sealed room. It is a permeable membrane, its boundary compressed by pressures we do not fully understand, its shield leaking particles outward, its edges visited periodically by objects and material from other stars entirely, carrying chemistries assembled under conditions we have never directly observed. We used to draw the solar system as a clean set of concentric circles in a textbook. The real structure looks more like a weather system, turbulent, asymmetric, breathing, exchanging material with the vast ocean of interstellar space that surrounds it. It is worth pausing here to reckon with the scale of what beyond the solar system even means, because human language is not built for these distances, and neither, honestly, is human imagination. Voyager 1, after 48 years of travel at roughly 17 kilometers every single second, has covered about 24 billion kilometers. If you shrank the sun down to the size of a basketball, Earth would be a grain of sand roughly 8 meters away, And Voyager, at that same scale, would be more than a mile down the road, and it still would not have reached the next star. At its current velocity, it would take Voyager roughly 17,000 years just to travel 1 light year, and the nearest star system, Proxima Centauri, is more than 4 light years away. Voyager is not close to another star. It is barely close to leaving its own front yard. And yet, at that almost negligible distance, it has already found a boundary that behaves in ways our best models did not anticipate. This is the part of the story that should genuinely unsettle you in the best possible way. Humanity built its picture of the edge of the solar system using nothing but light. Telescopes, radio waves, indirect measurements bounced back from unimaginable distances, decades of brilliant, careful, mathematically rigorous inference. And it was good work. It got broad strokes right. The existence of the heliopause, its approximate distance, the basic physics of a solar wind colliding with an interstellar medium. But the moment an actual physical object, a machine with actual instruments, punched through that boundary and started sending back direct measurements, nature immediately corrected the picture in ways nobody had fully anticipated. The magnetic field bent further than predicted. The plasma compressed in ways not fully explained. The shield leaked. This is not a story about how wrong scientists were. It is a story about the difference between modeling something from a distance and actually touching it, and about how every time humanity has made that leap, from the first ocean voyages to the first flights to the first spacecraft, reality has turned out to be richer and stranger than the map. There is a reason NASA has continued funding 2 aging plutonium-powered machines that have already technically completed their mission twice over. Voyager's plutonium power sources are decaying on a fixed schedule, and mission engineers have been forced, one instrument at a time, to shut down entire systems just to keep the spacecraft's critical hardware and radio transmitter alive a little longer. Heaters have been switched off in freezing conditions that would have destroyed the instruments decades ago, and against expectation, they kept working anyway. Engineers have had to relearn software written in assembly language from the 1970s, consulting retired colleagues and yellowed technical manuals, because almost nobody currently employed originally wrote the code running on either spacecraft. Every single one of these small human acts of persistence is the only reason we have any direct measurements from interstellar space at all. Without that stubbornness, everything we now know about the leak in our shield, the tilt in the galaxy's magnetic field, the mysterious compression at the edge of the sun's bubble would still be theoretical. It would still be a guess. And Voyager will not last forever. Within the next few years, one system after another will go dark, not because of some external anomaly, but because a radioactive power source built in the 1970s simply cannot generate electricity indefinitely. Estimates suggest Voyager's ability to transmit any data at all may not extend far beyond the end of this decade. When that final signal stops, arriving at Earth more than a full day after it was sent, humanity's only direct physical contact with the space beyond our star will go silent. And everything we learn afterward about interstellar space will once again be inference. Careful, brilliant, indirect inference. Exactly like it was before 2012. Until another spacecraft, someday, decades from now, makes the same crossing and tells us whether what Voyager found was a permanent feature of our solar system's edge, or a snapshot of one particular strange moment in a boundary that never stops moving. There is a broader question hovering behind all of this, one that every astrobiologist eventually has to confront, usually summarized by a single, deceptively simple observation made by the E across more than half a century of dedicated listening, no confirmed signal, no unambiguous transmission, no verified techno-signature has ever been found. Voyager's own anomalies matter here, quietly, because they demonstrate just how much of what we think we understand about the space around us is inference rather than direct observation. If our own solar system's nearest boundary held surprises, this significant, hidden in plain sight for decades until a physical probe finally arrived, it becomes a little easier to imagine how much more might be hiding across distances so vast that even light itself takes centuries or millennia to cross them. The silence Fermi described may simply reflect the limits of our listening equipment. It may reflect the staggering rarity of complex life. It may reflect distances so enormous that 2 civilizations could exist at the same time in the same galaxy and never have any realistic chance of detecting one another before one or both no longer exist. Nobody currently knows which explanation is correct, and that uncertainty is not a failure of science. It is an honest accounting of how little of the universe we have actually been able to touch. This is precisely why interstellar visitors like 3I Atlas matter so much to the search for answers, even when they turn out to be entirely natural. Every confirmed interstellar object is a tiny physical sample of chemistry assembled somewhere else, around some other star, under conditions we did not design and cannot fully predict. Cataloging enough of them, comparing their compositions, tracking how common or rare certain molecular ratios are across different visitors, gives scientists something no telescope pointed at a distant exoplanet can offer: actual material, however brief the encounter, that originated beyond our solar system and can be measured directly. Some astronomers have proposed that future missions could be designed specifically to intercept an interstellar object as it passes through, rather than merely observing it from a distance, in the hope of eventually returning a sample, or at least gathering close-up data far more detailed than anything a ground-based or orbital telescope alone could provide. No such mission currently exists, but the fact that it is being seriously discussed tells you how significant these fleeting visitors have become to the broader question of what other star systems actually produce. Widen the lens even further, and the story connects to one of the more profound reversals in the history of astronomy. For most of human history, the prevailing assumption was that planets themselves were rare, perhaps even unique to our own solar system. That assumption did not fully collapse until the 1990s, when astronomers confirmed the first planets orbiting stars other than the Sun. Since then, the number of confirmed exoplanets has grown into the thousands, and the diversity of worlds discovered has repeatedly outpaced what scientists expected to find. Planets have been confirmed orbiting 2 stars at once. Planets have been found with orbits so tight that a year lasts mere hours. Just this year, researchers using the James Webb Space Telescope identified a small world called L9859d, whose atmosphere carries unusual sulfur-rich gases above what appears to be a vast, long-lasting ocean of molten rock, a type of planet that fits none of the standard categories astronomers have relied on for decades. Every one of these discoveries follows the same pattern you have already seen twice in the story. A confident model, built from limited data, followed by direct observation that reveals something stranger, followed by a scramble to update the model. The universe does not seem to care how tidy our categories are. That thought should not be frightening. It should be clarifying, because every one of these findings, the plasma that should not be this compressed, the magnetic field bent 40 degrees off course, the shield with a leak in it, the interstellar visitor carrying chemistry assembled around a star we will never name, points to the same underlying truth. The boundary of home is not fixed, and it is not fully known, and the only reason we know as much as we do is because, half a century ago, a small group of engineers pointed 2 machines at the outer planets and then let curiosity carry them the rest of the way, far beyond anything the original mission ever asked of them. Consider, for a moment, what you're actually made of. The carbon in your cells, the oxygen in your blood, the calcium in your bones, all of it was forged inside the cores of stars that lived and died long before our sun ever ignited, scattered across the galaxy by supernova, drifting for billions of years through exactly the kind of interstellar medium Voyager is now measuring directly, before finally gathering into the cloud of gas and dust that became our solar system. In a very real physical sense, the strange, dense, compressed plasma at the edge of the heliosphere is made of the same category of material that eventually became you. You are not separate from that boundary. You are, chemically speaking, a former resident of it, temporarily arranged into something that can ask questions about where it came from. We built a machine to look at planets, and by accident, we built humanity's only physical witness to the true edge of our world. It has already rewritten what we thought we knew about the boundary between our star and the galaxy, and it is still out there right now, at this very moment, more than 24 billion kilometers away. Still listening, still transmitting, for however many years it has left. Somewhere between the compressed plasma at the edge of the heliosphere and the strange chemistry carried in by a comet born around a star we will never see. There is a much larger question waiting, one that no spacecraft has answered yet. How many more assumptions about the universe are we currently treating as settled fact, simply because no machine has traveled far enough, for long enough, to prove us wrong?